Okay, so section 2.5 on optimization is a section concerning applications of the techniques of calculus that you've learned so far. So you'll be given a situation, maybe it's a business venture, maybe it's an applied problem of some kind, and you have to turn it into a mathematical function that you can find the maximum or the minimum of. And so the first example is a parking lot built along the side of a road. Okay, so here's the road, and we assume that the edge of the road is a straight line. It doesn't quite look like it in my picture, but the edge of the road is a straight line. And we're going to build a parking lot using the road as one of the sides. So there's the parking lot. Now I'm going to assume it's a rectangle, and the dimensions of the parking lot, the length is going to be x and the width is going to be y. Okay, and the problem is, if I have 100 feet of fencing, what dimensions should I fence in to maximize the area? Because maximizing the area gives me the greatest potential revenue in terms of parked cars. You know, I'm going to charge a premium for the parked cars. Okay, so the first thing to do is to write down the function that we are going to be maximizing. And so the function is the surface area of the parking lot. And I'll write that down. The surface area is, it's the length times the width. It's x times y. And, well, that's a function of two variables, but in this course, what we're able to do really is find maximum and minimum of functions of one variable. So we need another relationship that relates x and y together. And we get that from the fact that there's 100 feet of fencing. So if you look at this diagram, you see that, well, we can use the fence for this side, and for this side. But we don't need to use the fence for the side that's for the road, the side that's the road. And what we know is that if I add up these three lengths, I should get 100 feet of fencing. And so that means that the other constraint, the other relationship, which we call a constraint, is that x plus 2y must be equal to 100. So the second equation is what we refer to as the constraint. And what we want to do next is use the second equation to eliminate one of the variables and plug that into the formula for the surface area. Okay, so if I move the 2y over to the other side of this constraint equation, by subtracting 2y from both sides, I get this relationship, x equals 100 minus 2y, and that's a formula for x that I can now substitute into this equation for the surface area. And what I find is that the surface area is now equal to 100 minus 2y times y, which I can, expand. I get 100y minus 2y squared. And as promised, this is a function of one variable, y. And so now I can just ask, can I find the maximum value of this surface area as a function of y? Now it's useful before embarking upon that next step to ask yourself, what is the range of relevant values of y? So what is the range of relevant values of the width of this parking lot? Maybe it's the height of the parking lot, but it's this dimension over here. And so clearly one limit is y can't be negative, and so you know that y has got to be greater than or equal to 0. And the other extreme is if x is 0, and if x is 0, then of course you have no surface area, but in that case you have to use all of the fence for this part and this part of the parking lot, and so each part must contribute to give you 100, and so the other limit is actually y is equal to 50. So now I'm trying to find the maximum value of this area function as a function of y, and y is ranging between 0 and 50. I'm looking for the absolute maximum of this function. So that means I can now apply the calculus tricks that we've learned before. So I'm going to take a derivative, set the derivative equal to 0, and look for all critical points. Here comes the derivative. So I've differentiated this and gotten 100 minus 4y, and I'm looking now for critical points. And that means I set a prime equal to 0. So 100 minus 4y equals 0. And I move the 4y over, and I get 100 equals 4y, or y is equal to 25. So if you remember, when you're trying to find an absolute maximum, the candidates for the location, for the value of y that corresponds to the absolute maximum, the candidates are the critical points. 25 is one candidate, and the endpoints of the interval where you're looking for the absolute maximum, which in this case are 0 and 50. So these are candidates. Okay, so we're on a new page now, and here's a summary of what we have so far. The area function is 100y minus 2y squared. That's written right here. We took a derivative, and we set the derivative equal to 0 and determined the candidate y values for the absolute max, and that was 0, 25, and 50. And now what you do is you plug each of these y values back into the area function. So a of 0, well, that's 0. I just plugged into this function up here where the arrow is. A of 25, okay, if I compute that area, it's 100 times 25 minus 2 times 25 squared, and that's 1,250. And then the area when y is when y is 50 is again 0. If I plug 50 into the area formula, I get 0. And so the maximum value is 1,250. That's the maximum area. And it is obtained by choosing y equals 25. And then if you go back and look up the formula for x, which is x equals 100 minus 2y, you find that the value for x is 100 minus 50 is 50. And that gives you the dimensions of the rectangle that maximizes the area for this problem with 100 feet of fencing, using the road as one of the sides of the parking lot. So one final comment about this problem is that I computed the critical points, then I considered the area at the endpoint 0, the endpoint 50, and the critical point 25. But there is another approach. Once you know there's exactly one critical point, if you just compute the second derivative of the function a, if the second derivative is positive, then the critical point is going to be your absolute minimum, and if the second derivative is negative, the critical point is going to be your absolute maximum. In this case, the second derivative, I'm just going to differentiate this formula for the first derivative up there, and the second derivative is finally negative 4, and since that's less than 0, we could actually conclude that this choice y equals 25 produces the absolute maximum value of the area function. Well, so here's a second example from section 2.5 in optimization. It is to minimize the product of two numbers subject to a constraint. So let me give a very precise example. So here's that same problem stated as a word problem. Of all numbers whose difference is 6, find the two that have the minimum product. So to start this problem, I have to choose variables. And so let's suppose that we're going to use x and y are the two numbers. Okay? Now, the thing we're trying to minimize is the product of these two numbers, and so I might as well write that down next. The thing we're trying to minimize is x times y. I'll give that a name q. And we're supposed to find the x and y that make this a minimum. So just like the previous problem, there are two variables, but we like to minimize functions of a single variable, and so we need a constraint. In this case, the other piece of information that we know is that the two numbers, their difference is 6, and so I can express that as a constraint x minus y equals 6. Well, that can be simplified, of course, to be written as x is equal to 6 plus y. And now I can once again use this relationship, x equals 6 plus y, in the formula for q, which becomes q equals 6 plus y times y, and that can be simplified to 6y plus y squared. So to find the minimum value of this product, I should take the first derivative, and set that equal to 0 to find critical points. So that becomes 6 plus 2y equals 0, which you can rewrite as 2y equals negative 6 or y equals negative 3. Now, once I know what the candidate value of y is, that also tells me what the value of x is, and in this case, that value is going to be x equals 3. Finally, in order to be sure that this value of y, negative 3, corresponds to a minimum of this function q, I should take the second derivative, and I'll do that over here. The second derivative of q is exactly equal to 2, and since that is positive, I know that this value of y corresponds to a minimum of the function q, and since it's the only critical point, I know it's an absolute minimum. The absolute minimum of q is, well, I have to plug the value y equals negative 3 into q, or just multiply x times y, and I get negative 3 times 3 is negative 9. Because q, which is x times y, is equal to 3 times negative 3, and that's 9. Okay, so summarizing, in this section on optimization, the first thing to do is figure out what function you should optimize. Remembering that you might need more than one variable, say x and y, in order to write down that function. If you really do have more than one variable, you need to find a constraint that connects the variables x and y. And once you find that constraint, you have to eliminate one of the variables in your original function. And once you've done that, you then have a function of one variable, and that's the function that you finally start looking at to try to identify either the maximum or the minimum value. And you do that by finding critical points, including endpoints, and then choosing the the value that obtains either the minimum or the maximum. And that's an outline of the procedure, and that concludes this video.